Welcome to Brain Vision.
because yeah, since there are no simple series or parallel connections in the circuit, so we will use Kirchhoff's loop rule and junction rule to write equations for the currents and for the voltages. So we write the junction rule at junction C and D. So we have I equal to I1 plus I3 at junction C, and I equals to I2 plus I4 at junction D, because I2 and I4 meet there and yeah, and give add to give I. So let's call this equation 1, let's call this equation 2. And then we write loop equations for each of these three loops. So we have Q1 over C1. So we set the current through the capacitor equal to the derivative of the charge on the capacitor, but we will do that afterwards, after we have wrote down the loop rules. And then we have another one. So I have like there are a lot of similar examples being done in the previous problems, so I'm not gonna explain step by step everything in order to save some time. So yeah, so let's call these three equation 3, 4, 5. So now I'm gonna just guide you through all the steps one by one. So first we differentiate equation 3 with respect to time, and then we set this charge q1 and q2 in these three equations equal to, so yes, then we set the derivative of these two charges as equal to current. So we have, let's differentiate equation 3 first. So we have, now we set the different derivative of these two charges as the current flowing through the capacitors. So yeah, one more thing. So the EMF is a constant. So the derivative of this EMF is going to be zero. Now dq1 over dt is the current flowing through C1, which is I1. So we write I1 in place of that, and similarly dq2 over dt is I2. So this gives I2 equal to negative I1 C2 over C1. So now we have one relation. So now we do substitute. Now what we do, we substitute equation 1 in equation 2 in order to eliminate this I. So we will get I1 plus I3 equal to I2 plus I4 from that. And since we have I2 and I1, since we have I2 expressed in terms of I1, so we will substitute that over here. So we get I1 plus I3 equal to negative I1 C2 over C1 plus I4. Now let's eliminate equation 4 and 5. Uh, now let's use equation 4 and 5 to eliminate I3 and I4. So from that we get I3 equal to Q1 over R3C1. So we get this from equation 4, and we get I4 equal to Q2 over R4C2 from equation 5. So now we plug these two in this equation, and doing that we get I1 plus Q1 R3C1 equal to negative I1 C2 over C1 plus Q2 over R4 C2. So finally we eliminate Q2 by using equation 3 here. So from equation 3, let me just write it. Where should I write? Let me write it next page. So from equation 3 we get Q2 equal to C2 times the EMF minus Q1 over C1. Yeah. Now we can substitute this over here in this equation. So if we do that, we get I1 plus Q1 over R3 C1 equal to negative I1 C2 over C1 plus 1 over R4 times EMF minus Q1 over C1. So from here we can write the EMF to be I1 R4 yeah. So this equation can be written as I1R plus Q1 over C, where we can say that R is equal to R4 times C1 plus C2 over C1, and C is equal to C1 times R3 over R4 plus R3. Let me just keep this whole thing inside a box. So this final equation represents a simple RC circuit with time constant tau equal to RC. So tau will be, so we plug these two R and C into tau equal to RC. So we get, doing that, and a little bit of simplification will give this expression. And if we plug all the values into this equation, so let's do that. So I'm here directly uh, plugging the C1 capacitor value of capacitance in units of microfarad because I know what units I'll get if I use this, but you need to convert, you might need to convert this microfarads into Faraday first. So because you know that Ohm's time Faraday is gives seconds. So ohm's time microfarad will give you microsecond, and I already know this. But if you are confused, just convert these into Faraday in order for your units to be consistent. So we solve this and we get tau to be 2.5 microseconds. Now again, so some of you might have questions as to why we wrote this like this. So we tried to convert this whole thing. We tried to write this in terms of a simple RC circuit with just a resistance R and capacitance C. So for that reason, we tried to write this expression as something like that, and then compared what R should be in that case and what the capacitance should be in that case.